Welcome back, AP Calc students. We're going to really take a look at our first example from our 8.2. Hopefully you had a chance to check out the introductory video. Now we're going to move into this example. This example is a calculator active question. It requires extensive use of the calculator, so you might want to have one handy. It says we got a particle that's moving along a horizontal line. For time 0 to 8, the velocity of the particle is given by v of t equaling t minus 3 ln t plus 2 plus 2t times the sine of t squared over 12. And the position is going to be given by s of t. It's known that s of 0 is negative 3. From this information, we can ask a whole slew of questions, and I'm just going to take them one at a time. Part A, find all the values of t in the interval from 4 to 7 for which the speed of the particle equals 5. There is no question that the calculator is going to get heavy use here, but that doesn't mean that the problem is necessarily easy. You still have to know these concepts that relate to the vocabulary, etc., the questions that's being asked, and so on. So speed is 5. We start there. We isolate on this. The speed is 5. Well, the first thing that you're going to have to do is connect the fact that speed probably has a little bit to do with velocity, but speed is not the same thing as velocity, and it's a very common misconception. We learned, hopefully we remember, maybe we need to be reminded, that speed is the absolute value of velocity. That's very important. So we are essentially going to set v equal to 5. And from that equation, we are just going to take whatever values that we get that lie between 4 and 7. And those would be the times for which that works. So let's move over to the graphing calculator and see how this all works. All right, once again, I am using the TI Nspire teacher software here. You can also replicate this problem if you're using a TI-84. A lot of the commands are somewhat similar. So the very first thing that I want to do is I want to define a function that I'm going to call speed. And I can get real fancy on the TI Nspire. Maybe I want to call this SPEED. I don't know. I could do something along those lines. And I could say the speed function of time t is equivalent to the absolute value of the v. I could do that, but I'll tell you what I'm going to do instead. I'd like to use a little bit more thinking behind what speed is in relation to velocity. And maybe in this problem later on, I may not need speed anymore. Maybe velocity will get used quite a bit. So why don't we do this? Let's define the velocity. So we're going to take the velocity and we're going to hit our control math template to get our colon equal. And then we're going to type in this expression, which is t minus 3 times the natural log control e to the x, t plus 2 times t, and this will be multiplied by the sine of the quantity fraction t squared, let's do that correctly, t squared over 12. If you're using a TI-84, you're going to enter the same expression as the y1 function. Your variable will be x instead of t. So it looks like we've got everything that we need here. We're going to hit enter, make sure that it's matching the question that's on our page. And then, because we have a CAS calculator, we can try something. Now, try is the key word here. We know that we do have an algebra feature. CAS calculators can be pretty cool. We could try to solve the absolute value, which to get absolute values, we'll need to type in our math template to get that particular symbol. And then we'll put our v of t. Oh, it's bold. The calculator understands it. We'll set that equal to 5. We'll say, calculator, solve this for t. And then this really cool thing that I've taught my students in the past is we can put this such that afterwards and restrict our values of t to land between the 4 and the 7. So I'll just type in 4 less than or equal to t less than or equal to 7. Let's hit enter and see what happens. And it seems like we have a favorable response. T is 5.62, T is 6.5, but neither one of those happens to be on our interval 4 to 7. Did I say neither one? I meant to say both of those are on our interval 4 to 7. So in other words, it looks like there's going to be 2 times when the speed is equal to 5. Now, sometimes we can get this little warning symbol, which just basically says more solutions may exist, and that's a little scary sometimes. I've seen certain issues where the calculator is just not capable of solving the complex equation that we put into it. So what I would suggest is to do what most people have to do that use the TI-84 or a non-CAS calculator, and let's go to a graphing page, and let's graph the absolute value of this velocity function, which I stored. Now take a look. If we enter this, we have to use the variable x, and I've shown this in other videos. And the cool thing about it is if you type an x there, it's going to take all of the t's that we had already entered and boom, switch them over to x's. So how cool is that? Next, we can isolate in on this window a little bit. We probably don't need this massive size, so we can maybe go -2. That way we can see the y-axis. I'll take this out to about 8, scale of 1. Likewise, we don't typically have too many negative speeds in this particular instance. We'll go up to probably about 10, scale of 1, and that's probably going to be good enough for us. All right. If those of you using a TI-84, you probably are already to this step because all you had to do is hit your graph button. And of course, you can change your window as well. Now, what you're going to have to do is graph the other equation, 5, in a separate window, y2 or f of 2 of x, in a separate line, same window. And this one turns out to be red here on the Inspire. And we notice that these two ordered pairs, I think, are both between 4 and 7. Here's where 4 is. 7 is behind it's right up there, is where the 7 is. So I think we're going to be okay. So we can go ahead and hit Menu, Analyze Graph, do our intersection, and boom, there's our first answer. And boom, our second answer. And let's go ahead and get one more here. Boom, a third intersection. Now notice there are 3 intersections, but poor 3.65 is going to get thrown away. And the reason that we're going to get rid of this is because we have to take only the values that are between 4 and 7. And so the two values that you have right here, their t values correspond exactly to what we found when we used the CAS capabilities. So we'll record those in our problem. We only are required to write our answers to 3 decimal places. A lot of times what I like to do, though, is to write them to maybe a 4th decimal place, just to get a little bit more accuracy at times if I'm going to use those again later on. But for now, I'm just going to keep them at 3 decimal places written, and if I need them, they're always stored into my calculator. All right, there's part A. Part B, write the expression involving an integral that gives the position s of t, and use this expression to find the position of the particle at time 3. This is a really neat application of some of the things that you learned in Unit 6. Basically, what we want to do is say, we know for sure that s of t is our good friend, the position. But we also know that this position has a very beginning value of -3. So we will just state that we are starting at -3, our initial amount, and then from there we will add an accumulation that is an integral that starts at time 0 and ends, where do you think? Well, you would think at 3, right? But if we want to write an expression that gives the position at any time t, then what we might want to do is use the t as the upper boundary there, and then throw in our velocity equation, and then be mindful of the fact that it's more proper mathematically to not use the letter t a second time here, and thus use a dummy variable instead. On the AP exam, we kind of look the other way. Besides, a t and an x look awfully lot alike if you tilt your head, but mathematically it probably makes a little bit more sense if they're different, but it's not a deal breaker if they're the same. So we're going to go ahead and stick with that as our S of t. Now, if we want to find out, okay, well, where are we at time 3? Then all we have to do, as you can probably guess, plug 3 in for the t. And so we have -3 plus the integral from 0 to 3 of v of x with respect to x. And this is probably going to be some decimal. Let's find out what it is by going back to the calculator. And notice that this v of t is already defined. How cool is that? Because all you have to do now is type in -3 plus. We'll do a shift plus to get the definite integral. You might be doing a math 9 if you're using a TI-84. And we go 0 to 3 of v. Now I would go ahead and just stick with the variable x, or the variable t, since that's what we defined it as. Hit enter. There is an answer for you. How about a control enter to get a decimal approximation? And that is correct. -6.263, we're going to call it. -2.263 is going to tell us basically where the position is approximately at time 3. So this particle's moved like to the left of the origin, let's say. All right, part C. Find all the times t in the interval 0 to 8 at which the particle changes directions. You must justify your answer. All right, let's think about changing directions. What happens when that occurs? Velocity might be positive, then velocity might be negative, right? Because moving left is a negative velocity, moving right is a positive velocity. So in order to determine if your velocity is going to change signs and thus your particle changes directions, you first of all have to make sure you know when does the velocity equal 0, right? So that's your first goal. And because we've already graphed our velocity, or absolute value of velocity, we could probably take a look at just the plain old graph of velocity and determine these pieces of information. So let's go back to the calculator. And I'm going to go over to the calculator page, the graphing page, sorry. And I tell you what I'm going to do is I'm going to call up by hitting the tab shortcut that f of 1 of 5, and I'm going to get rid of it. I don't want the absolute value of v of x. I want v of x, period. And then I don't think we want that y equal 5 anymore, so we can get rid of him. And so this is the graph. Let's move myself out of the way. It is the graph that goes from 0 to 8, right? You can see the interval 0 to 8 nicely here, very nicely, 0 to 8. And we can see that this graph does have a sign change of the velocity on 2 occasions. So we're just going to go into our menu, analyze graph, and we're going to compute what's called a 0. And we still do our left bound over to our right bound. We do the same thing again. If you find that I'm going a little too fast, please feel free to pause the video. And those are going to be our 2 values of t for which the velocity not only equals 0, but changes signs. Now it's going to be important to make sure that we communicate that. So v of t equals 0. And furthermore, v of t changes signs. Now, if you just say v of t changes signs, basically the intermediate value theorem suggests that v of t is equal to 0, and you wouldn't necessarily have to say that, but it is powerful to mention both. And then you would say at t approximately, and we have 2.341, and t is 6.127 seconds. And one last time, I'm going to corroborate that with my graph just to make sure. 2.341 after I rounded, and 6.127 after I truncated. All right, we're almost there. We got one part to look at. Is the speed of the particle increasing or decreasing at time 7? Give a reason for your answer. This is a concept that it's been a while since we've talked about, but speed increase decrease is built upon a couple of ideas. You have to know, first of all, what is the value of the velocity at this time 7, and you're going to have to figure out what is the value of your acceleration at that time. Because if you remember, if acceleration and velocity have the same sign, they're working together, and you have a particle that's speeding up, whether it's to the left or the right. But if velocity and acceleration have opposite signs, they are opposing each other, and that will cause slowing down. Now, all of this is all ready to go in the calculator. Again, we'll move over to the calculator page, and I think I've got quite a bit of a mess going on here, but we're still going to be fine. I don't want to clear it because I don't want to get rid of the definition or the defining storing of the v of x. So what we're going to do is we're going to start with that v of x or v of t, and I'm going to type in a 7. I'm going to put a decimal after it. I learned my lesson. I want that decimal there so that I will get a nice decimal value, and the answer is negative 10.911. Now, just so you know, I am in radians. That's very important. If you were getting some answers that were a little different, you might want to check, because degrees would be a bad thing to be in right now. So negative 10.91, I'll tell you what, why don't we round that to negative 10.918? We really don't have the ability to put units here. A lot of times students will force the units, say, units per time. It's not required. If we don't give you units in the problem, you don't have to start making things up. Now let's find a of 7. Again, we're going to use the calculator. Why? Because this derivative is way too nasty to take by hand. And besides, you're still demonstrating that you know calculus, even though you're using the calculator. So the shortcut to a derivative on the TI Inspire is shift minus. Some of you out there using a TI-84 might be hitting math 8 at this point. We'll take our derivative with respect to t of the v of t, and then I want to make sure that I say when I want this derivative to be taken. So I just like to throw in the such that t equal 7. There is a variety of ways to do this. There are a variety of ways, I should say. This is one of my personal favorites, but you can investigate other syntax methods. This pretty much is the fewest keystrokes, though. And I get negative 10.561. And so we'll write that up, and that indeed is our acceleration. Now you have some very powerful evidence here. Because the velocity and acceleration have the same sign, you can say that the speed is increasing. I want you to think about that for a little bit. So the speed is increasing. I'm going to use some abbreviations here. I personally don't advocate abbreviating on the AP exam. I think so much is at stake for this 3-hour test that you're going to take. Write the words out. If it means college credit, it's certainly worth your time and effort to do that. The speed is increasing at t equals 7 seconds. And because the reasoning, I'll abbreviate because, and we'll say A of 7 and V of 7 are, we'll say both negative. How's that? You could say both less than 0. You could say a variety of things, but if I abbreviate, this is going to be perfectly fine. If you said A of 7 and V of 7 have the same sign, it's okay, especially with the evidence of what A and V are in the corner there. It's just a lot more powerful when you are speaking in specifics. And that will take care of this free response question that has quite a bit of impact as far as the AP exam is concerned. Before we go away, there's one little thing I wanted to do about part D. Speed increasing, decreasing at time 7. Check this out. You might like it. Some of you might have been thinking, wait a minute, what if I would have graphed the speed? Okay, well, let's do that. Remember our good friend V of X? Well, if I highlight him, I think I can go back and I can insert those absolute values and then boom, yep, that's what he looked like from before. Where is 7 at? Well, let me get rid of a few things here because they're kind of just in my way. If I go to where 7 is on this curve, 3, 4, 5, 6, 7. Wow, that's right here, isn't it? 1, 2, 3, 4, 5, 6, 7. That's right. Oh, that's up here. It's like next to my picture. It's like right about there, maybe. Yeah, right at that point. Wouldn't you say that the graph is increasing there? So it's another way that you could visualize the fact that acceleration and velocity having the same sign is going to cause an increasing graph of the absolute value. So you can think about that as another way to put all the pieces together. Anyway, I hope this helps. We have a couple of more problems coming up in Unit 4 that are Unit 8, Topic 2, that have a lot of great connections to what we call PVA, position, velocity, acceleration. So be sure to check those out. We'll see you next time.